In this video, we're going to be talking about exponential functions and exponential growths. So look at this newspaper. I have a newspaper here. The thickness is about 0.1 millimeter, as you see on the screen. And I'm going to take this newspaper, I'm going to rip it in half. As so. And I'm going to stack these two on top of each other. So now we have this thickness. I'm going to rip it one more time. So I'm ripping both of these halves. And now I have 4/4. So this is after 2 rips. I have this thickness. So how thick do you think the stack of papers would be after 3 rips? I'm going to do one more rip here. So here is my stack. Is it going to be the thickness of a fingernail, the width of a hand, thumb included, as tall as an average person, or as high as a 2-story house? Well, when you're thinking about that, let's rip some more. So what do you think is going to happen after 10 reps? So that was 3, 4, 5, having a hard time ripping it now. 6. I think I'm only going to get 6 rips in, so I'm like right here. So if I ripped it 10 times, how tall do you think it would be now? What about 50 times? After 50 rips, I'm just stacking it up. Remember, it's only 0.1 millimeter thick. I'm going to keep ripping and ripping. It turns out that this experiment is a great example of exponential growth. So if we rip this paper 3 times, it would be about the length of my fingernail. So the thickness right here. Ripping it 10 times, I'm already to the width of my hand, including my thumb. And if I ripped it 50 times, we're already over a person's average height. A 2-story house, the Sears Tower, it's going to be about the distance to the sun, where I ripped it 50 times. So you can see with exponential growth, if we put a 50 in for our input, we would get a distance of 95 million miles, the distance to the sun, with just ripping a 0.1 millimeter sheet of paper. So I think that this sort of shows the magnitude of our exponential functions. So let's go ahead and look at some of these. Our first exponential functions will be of exponential growth. So an exponential function is different than the functions we've studied because we have y, the function is equal to a to the x. So our input is in the exponent, which we have studied in previous classes, and we previewed at the first part of this class. But it's important because now we're going to study these functions where our input will be in the exponent. Here we're going to be looking at where a is greater than 1 and a is not 0. Remember, if a is 0, then you just have a boring function, the x-axis. And if a is greater than 1, our base is going to be positive. So when we plug in a power, it's going to be a positive fraction greater than 1. This thing is going to grow. So if I plugged in 0 for something like this, I would get a to the 0, and anything to the 0 power is 1. So when we're making our graphs, we have this point 0, 1. What can I not plug into this function? So can I take a number to any power? What about a negative power? If I take a number to a negative power, that just flips the fraction, right? It takes the reciprocal. So it turns out that I can actually plug in anything into this exponential function. So it's going to be all real numbers, or if you like, negative infinity to infinity. But what am I going to get out? Even if I flipped a number and it got smaller and smaller and smaller, it's never going to get less than 0. So my range is going to be 0 to infinity. It turns out, like, if I had, let's say, 2 to the negative billion power, it'd be 1 over 2 to the billion. Very close to 0, but not quite. So we're going to have a horizontal asymptote here at y is equal to 0. So these are all properties of this basic function that we're going to be learning about. And the function for a being greater than 1 is going to be increasing. It's going to be getting bigger and bigger and bigger. So in fact, up here, I should say that a is greater than 0, because we can have those that are between 0 and 1, but we're going to be looking at a is equal to 1 first. So let's go ahead and try to plot these functions here. We do know that we have that horizontal asymptote here at the x-axis. We have the point 0, 1. Let's try 2 to the x. What if I plugged in 1 for x? I would get 2 to the first. That's going to be 2. What if I plug in 2 for x? I get f of 2 is equal to 2 squared, or 4. So you can sort of see this is like the ripping paper. If I did 3 rips, I'm going to be 8 times as much. If I could somehow rip it negative number of times, so if I had 2 to the negative 1, that flips the 2 and makes that 1/2. 2 to the negative 2, that flips and takes it squared, so that'd be negative 2 comma 1/4, negative 3 comma 1/8, and so on. So it does go into 0 very quickly to the left, but the right-hand behavior is going to go up quickly to infinity. In fact, this is one of the quickest functions that we will study in this course. What about 3 to the x? In the case of 3 to the x, everything is going to be tripled. So again, if I plug in 0, I'm always going to get 1 there. It's going to go through this same point. Let's illustrate with a different color. If I plug in 1 for 3 to the x, I get 3 to the first, or 3. If I plug in 2, I get 3 squared, or 9. So this is going up really quickly. And it's going to go to 0 quickly. If I plug in negative 1, that's 1/3. Negative 2 is 1/9. And that sucker is going into the asymptote really quickly there. So the larger my base is, the quicker it's going to go to infinity. There are my two functions. We can sort of look at this graphically. So if I plugged in the function, I would have 2, and then I would do a caret. So I'm going to be using my caret button here, 2 raised to the x. And then I'll plot 3 raised to the x. And we'll graph these. We should see pretty similar result. There's 2 to the x, and 3 to the x should rise a little bit quicker. There it goes. It does. Okay, so those are very similar results to what we have here. And notice that it never does get lower than 0 in terms of the range. What happens if we have bases that are less than 1? Let's take a look. So if our base is less than 1, like 1/2, still, if I plug in 0, I'm going to get 1/2 to the 0, which is 1. The domain is still going to be all real numbers. My range will still be just positive numbers. And my horizontal asymptote will still be at y is equal to 0. But in this case, everything sort of gets flipped about that y-axis. So the function is going to be decreasing on its domain. So I'm going to write in that asymptote here, and we'll sort of discuss why this happens. So again, I plug in 0, I get 1. If I plug in 1 this time, I get 1/2. If I plug in 2, I get 1 squared over 2 squared, which is 1/4. If I plug in 3, I get 1/8. And this thing is going down to 0. However, if I plug in -1, what happens is this flips, and I get 2 to the first, which is 2. If I plug in -2, this flips again, so I get 2 over 1, but the squared is 4 over 1, which is 4. So 1/2 to the x is going to be the same as what we had for 2 to the x, but it's going to be flipped about the y-axis. And we can illustrate why that happens with y is equal to 1/3 of x. So if you think about 1/3, we're going to be looking at rules of exponents, but 1/3 could also be written as 3 to the -1. Remember, if I have 3 or a number to the -1 power, that just flips it. So it's going to be the same thing. And now if I have powers, I can have a power to a power, they multiply, so I get 3 to the -x. So this is just going to be like the 3 to the x we saw on this screen here, but it's going to be negative, so we're going to flip about the y-axis. So everything should be switched over here. I would have -1/3, -2/9, and I would have 1/1/3, 2/1/9. And my function here with negative base is going to decrease very quickly to the asymptote. And just to sort of show you, if I replace that 2x by, let's say, 1/3 raised to the x, we should see two graphs that are similar, but just reflected about the y-axis here. So the first one is going to be the one we just plotted. Y is equal to 1/3 to the x. And the next one is going to be y is equal to 3 to the x. And hopefully this sort of illustrates why that's happening. Okay, we're going to be looking at some more properties here in just a minute. I'd like you to recall some properties that we have about exponents. So when we multiply two exponents together with the same base, that turns into adding those exponents, so we get a to the x plus y. If we divide those exponents with the same base, we're subtracting the powers, so that would be a to the x minus y. Just as we saw in the previous screen, if you have a power to a power, we multiply those powers together. And also, as you saw in the previous screen, if you have a negative power, that actually flips that power, makes it positive down to the denominator. So we're going to be looking at the basic graphs and see how these shifts are going to work out with our basic graph here. So let me see if I can get everything on here very close. Okay, so I'm looking at the function f of x is equal to 3 to the x. What's going to happen if I'm looking at 3 to the x plus 2? Notice this x plus 2 is an inside change. And with inside changes, things do the opposite of what we think. So an additive inside change is going to move the function left 2 units. What if we have an additive outside change? This one should move the function, so this is very intuitive, up 1 unit. Now for the next couple, we have things that aren't in terms of the original function, but I'm going to conveniently use this idea of negative exponents to turn it into the original function. So if I have 1 over 3 to the minus x, I can change that into 3 to the x by just flipping this up to the numerator. This would be negative 2 plus 3 to the positive x. So when I have a negative exponent, that flips it up into the numerator denominator and it makes that exponent positive. So here, this is going to move the function down 2 units because it's an outside change. Finally, I have one more here, and that is 1/3 to the negative x plus 1, if you can see that. What I'm going to do here is I'm going to factor that negative out. I'm going to make this 1/3 to the negative, and if I factor out a negative to the negative x plus 1, I get x minus 1. And so 1/3 to the negative x minus 1, I'm going to take that 1/3 to the negative 1, and I'm going to make that 3. So I'm turning that negative power I have here, I'm going to actually use that to make this 3 by this rule here. So when I have a to the negative 1, I just flip that and I get 3 over 1. So that's going to be 3 to the x minus 1. And now we know that's an inside change. So this is going to move the function right 1 unit. Let's see how this works out with the graph. So I started out with the original function, and then I have this number b in there. So that's going to hopefully move the function up 1 unit. And when we move the function up and down, it's going to change the asymptote too. So the asymptote is also going to move up 1, and the range will be affected. Great. Now I'm going to try a, which is 3 to the x plus 2. And notice here, the x plus 2 is in the input. I'm going to get rid of that one. So now what we should see is the function moving to the left 2. So we have the original function, and this is number a. So we should be moving to the left 2 units. Let's see if that's true. And there it is. Yep. And notice when we move left or right here, the range doesn't change. We still have 0 to infinity. Let's look at C. So C, the original that we have there was -2 plus 1 divided by 3 to the negative x. So if I have that in there right, what it should do is it should move that function down to, there's my original, and it does move down to, so my asymptote and the range is going to move down to as well. So that domain now would be -2 to infinity. And finally, I'm going to use this function here. So this is going to be parentheses 1/3 raised to the parentheses negative x plus 1. Now I'll just delete the rest of this out. And what we should find out here, negative x plus 1. Let me try that again there. Negative x plus 1. Okay. What should happen here is we should move the function just to the right one. That's not going to change our domain at all, but it should move the function to the right one. So that red one should be to the right. Oops, it looks like I need to re-enter that in. So I need to get rid of that. And I don't need these parentheses here. Let's try that. Whew. All right, it did move to the right one, just like we thought. So in general, when we have a exponential functions, you know what, things happen just like we learn with other functions. So in general, an additive inside change, a to the x plus or minus b, shifts the function either left if we have positive or right. Those are the inside changes. The outside change, so a to the x plus or minus b on the outside, is going to move the function up or down. Okay, so that's more about the graphs. Finally, some of these easier exponential equations we can solve by using the fact that our exponential functions are one-to-one. What that means is they pass the horizontal line test, and you could see that from the other page when we graph those. So it turns out if we can get two exponential functions with the same base, we can set their inputs, which would be the exponents equal to each other. So here I want to use those rules of exponents um, to solve the equations, and we're going to know that these functions are one-to-one. So we're going to use the fact that when we can get those same bases equal to each other, their exponents will be equal to each other. I have 5 to the x is equal to 625. Can I write 625 to a power as a power of 5? Well, we can we know that 5 squared is 25, and 25 times 5 is 125. What about 5 to the fourth? 625. So yeah, we can rewrite 625 as 5 to the fourth. Now, since these are equal to each other, and they have the same base, we can use the fact that they're one-to-one to set those exponents equal to each other, and x is equal to 4 in this case. So we only get one answer there because they're one-to-one. Okay, what about 64? We can write that as 4 to a power, right? 64, isn't that just 4 cubed? It sure is. So I'm going to replace that 64 by 4 cubed. And now I'm going to use the rules of exponents to, when I have a power raised to a power, we multiply those together, right? So I have 4 to the 3 over x is equal to 4, and that power would be a 1. Since these exponential functions have the same base, I can go ahead and I can set the powers equal to each other. And then I can go ahead and solve. So I could think about this as a ratio. So x times 1 is equal to 3 times 1, and x is equal to 3. All right. Sometimes we have to do a little bit of legwork, like on C, to actually get these equal to each other and then find the same base. So what I'm going to do is I'm going to subtract that negative 1/49th over and make that a positive 1/49. I do know that 49 is 7 times 7, so this is 1 over 7 squared. I also know that I want the 7 as the base. Here I have 1 over 7. I need to move that up into the numerator, so I'm going to make this 7 to the minus 2 and move it up. Now notice we have those two equal to each other. They have the same base, so I can set their exponents equal. 2x is equal to negative 2, and dividing by 2. This one gives us x is equal to negative 1. And if I should plug this back into The equation, I would get 7 to the 2 times -1, that's -2. 7 to the -2 flips 1 over 7, squares it 1/49, minus 1/49 is 0. So these should all check out. All right. So I hope this gives you a little more insight about exponential functions.